there is a hidden sum here. So T of the sum is the sum of the difference. You get this. And what are these? So you can give them any name. Okay, so these are, maybe I can call this as this is my TI. And VI. Okay. So I can say that these guys are what? These guys are the components of the tensor. Okay? So these guys are the intrinsic part of the tensor. This is not. This is the intrinsic part of a vector actually. Well, these are the intrinsic part of the tensor and they are going to stay with the T no matter what V you choose actually. So they are kind of fixed. So you call these are the components of the linear transform. So you learned this kind of a thing when you were learning the back. Question: can we do something like similar here? Okay. The answer is why not. Let's do it for one particular case. Okay, let's not complicate our life. Let's do it for the 1-1 tensor. So what would be 1-1 tensor?
Map from V cross V.
So it's a map from V cross V star. V cross V star. Okay. So it's a map that swallows a vector and a covector and gives you a number. So let's operate T onto U and alpha. Okay? Where U is what? It's an element here. Okay? It's an element here. And alpha is what? It's an element here. Okay? Question: what would be the components of T? How does the component of this is going to look like? And for knowing this, what we need to do, we have to write it as
U can be
this would be UI, EI, okay,
comma
alpha I.
alpha I,
some alpha I,
and then
epsilon I. You have to keep one thing in head. So when you are writing vectors,
you
okay,
standard base.
the bases are covariant, so therefore their components are down. But their components are contravariant, so therefore you are putting an index above. While you have exact opposite when you are doing or dealing with the covector cycle, that the bases are contravariant,
The components are
or the
covariant.
components are covariant. You got this. And how can I know it? So what would be this? So this would be, how can I write it? So TUV would be,
सर वो फर्स्ट कंपोनेंट की linearity यूज करें और सेकंड कंपोनेंट की linearity.
so I'm going to get, so T is operating it onto this ordered pair actually.
UI. सर UI
This
बाहर
UI
आएगा ना सर.
Sir, bracket में.
and the T of EI, bracket नहीं आएगी?
कहाँ सर दूसरा कंपोनेंट
Sir, R में जाएगा ना तो ये.
So that's a number. So that's a number. So it's going to be UI
Times
T times EI.
T times EI. ठीक है? And
कहाँ
प्लस आएगा.
नहीं यार.
अंदर कम आएगी वाकई से.
you have, so unless we don't know the definition of it, we can't, write it
Sir, so
explicitly.
we can write it as U of I, UI, alpha I, then T of EI, comma epsilon I.
Let's write it this way. So
UI,
UI,
alpha I,
and
T of
T of
EI, comma.
EI and epsilon I. So
This is going to be a number.
take it. And let's give this name. Okay. So one of the confusion. Let's not put I on both
Yes,
indices.
J.
So put a J here and put a J here.
So that we can know
You're
the.
gonna have a J here and you're gonna have a J here actually. Okay. So let's give this, if I want to give this name, what name should I give? So you have to always respect the order.
ij.
So the, I below and J above actually. So you have to respect the order as well, and this is important. Okay? You can say that I can put ij here, okay, the way I want, yes, okay? You have to respect the order. And then, so finally what do you get? You get Tij and Ui alpha j, and it makes sense actually. Through summation convention, think about it. So j and j and I actually. So this is the sum actually essentially. Are you getting the point? So you call these as the components of the tensor. Okay? So usually what happens essentially, okay, is that the physicists are not interested in these quantities actually. Okay? So they just want to focus on these components actually. So the understanding, as you can understand the vectors in the terms of a component, okay, so they usually just understand the tensors by using their component. Okay? While these quantities are also important, and we're going to see that why they are important actually. Why they don't do it, practically they do it good because, we're going to see afterwards that if you have this, you have almost everything. So, if you ignore even this part, it's fine. Okay? But, for a mathematician, for us, like this is important that there is something, multiplied with it. So you have to keep a track of that as well actually. Okay, we can later on ignore it when we are doing computations, but at the moment we have to keep that. Okay? Is it making sense? So now you can do something similar. So what do you think? What you're gonna get if you have this? So if you write, this as a, such kind of an expression, how does it going to look like? So it is going to have, R, superscripts, contravariant components, and S covariant components. So how does it going to look like? So let's give them a name. I1, I2, and IR. And then, for example, J1, J2, and JS. And there will be things multiplied with it, like this. Okay. So you're going to have U, okay, I1,
UI2
I2, IR,
times
and
alpha
alpha
J1
J1 down, alpha JS. So this is going to be such kind of thing. While this quantity is essentially we call the components of the tensors. Yes. So I'm just writing a rough sketch. Okay, you can make it formal and but it's going to be looked at. Such kind of a quantity is going to appear. Okay. So what are tensors? Tensors are nothing. They are linear maps. Okay. Some kind of linear maps, actually. Multilinear maps. Okay. And you can see that you can combine a hell lot of kind of things into one bucket actually. If you define things. So in other words, a thing can be intrinsically something, okay, but it could be a tensor at the same time as well. For example, we talked about inner product. Okay, inner product is something else. It just kind of measures the angle between two abstract vectors. Okay, but we can also see this as a tensor actually. So it kind of unifies lots of theory. Okay. Are we happy with this? So let's move on. I want to make these things even more rigorous. So let me define some things called the tensor products. And then the tensor spaces actually. Tensor products. So, same notation, I have a vector space V, finite dimensional, and what? A rule of it. By the way, you can see actually that for defining all this machinery, we haven't used the finite dimensionality of the V actually. Okay? We have used it when you are writing it as
Basis.
basis actually. Okay, so you have used it. So at the moment we are using it. But we can relax these assumptions as well. Okay? Because all these bases are Hamel bases actually. But you can replace them with the notion of what we call the Schauder basis. In other words, where these sums are not infinite, but they are not finite, but they are infinite actually. So in other words, so a vector is not sum of a finite things; it's sum of infinite things actually. But the trouble with that would be that then you need a notion of convergence, because that infinite sum should make sense actually, and hence you need a topology. Okay. So far you don't need topology here, so we are happy with this. But if you want to extend it more, you need some version of topology on them. So what are tensor products? Simple. Let's have a vector space V, and its dual V star. Okay. Finite dimensional, and let's create. Okay, I want to create what? I want to create a linear map from V cross V into R. Okay, here I have abstractly defined it. So I have defined tensors, not created them. Question, can we create them? Using purely, so I don't want to go outside V and V star, so I want to do things within V and V star actually. So I want to create a linear map, but purely using V and V star, nothing else. So I want to map here. How can I do it? I know that there are linear maps here.
From V to R.
Okay, so maybe we can get some help from there. So let's take some covectors. In other words, take some alpha and beta from V star. Okay. Question: can we create a linear map using these two covectors? Okay. So let's create a linear map using these two covectors actually. Okay. And again, as I said that I don't want to use external information. I want to live here for now. Okay? I will need more information, beside all these, but at the moment not now. So let me have a map, okay, which kind of takes two vectors, say UV, and gives me a number.
Alpha U plus beta.
Okay, so if you have two vectors and two maps, so in other words, using these inputs, how can I create a number?
Sum of these.
So either you can do sum, or you can do product, but you have to make sure
Linear.
that they must be linear.
So some.
So linearity should be there.
Sum.
Okay. So here's a trick. Consider this, for example. alpha of u, beta of v, beta of u, alpha of v doesn't matter. Okay, so let's take beta of u multiplied by, say, alpha of v, but you can do other way around as well. Doesn't make sense. So that's another. Now, if you have such a map, you can see that this map is going to be multilinear as well. Would that be multilinear? Think about it. So if I have u1 plus u2 and v, so it's going to be what?
Beta of
Beta of
Beta of u1 plus u2 and alpha of v, but since beta is linear, so you have all these properties. Okay, so you can check all these properties. Check this is bilinear. Check this is bilinear. So we took two covectors and created a bilinear map. And let's give this bilinear map a name. So since the name, since like the map is depending on a defined through beta and alpha, so naturally beta and alpha should be there. Okay. But you are defining things on a product, so let's give it a name, tensor product. Okay. So on v cross v, what do we mean by, so it's like, what do we mean by taking two vectors and having their tensor product? Basically we are saying that it's a kind of a map. So the tensor product is kind of a bilinear map from v cross v into R. Are you getting the point? Okay. And this tensor product of two bilinear maps is a tensor itself. What is the rank of this tensor? 2, 0. So it's 2, 0 tensor. Are you getting the point? Okay. Let's collect all such tensor products.
beta and alpha belongs to
So it's like alpha comma beta belongs to V.
V star.
Huh?
V star.
So it would not be V star.
No, sir, alpha and beta
but this
belong
will
to
be
V.
V star. Okay, so these are from V star. So let's give it a name. So the name should be what? What do you think? What should be the appropriate name for it? The natural one. So these are the bilinear maps. So what should be the name for it? So if you have a linear map from V into R, you are putting it into the V star. So now you have a maps from
V star square.
not V star square, okay. But how about giving this name? V star tensor product V star. This should be a good name. Okay. So taking the tensor product V star. Are you getting the point?
Is it a vector space?
Yes, you can ask a next question. Is it a vector space?
What will be the basis?
Okay. What will be the basis that you can ask a hell lot of new interesting questions. Okay. Does those bases are going to have some relationship with the basis of V and V star? There must be. Okay. So is this a vector space? Answer is yes. Why not? Why it shouldn't be? So in other words, if I take say a bilinear map, beta alpha, and I take another map, give me gamma, tensor product delta, okay, and I want to add them in some sense, and I want to operate them on
Some UV.
some UV, okay, elements of V. The question is, what must be the
Beta class.
just
Beta class alpha.
addition. So take the beta,
Class alpha.
the tensor product of beta and alpha,
operated
operate it onto UV
Plus
plus
delta class or gamma class.
tensor product of gamma
delta
and delta
operated
operated onto U and V. Okay? This must be the definition. You can show that this is well defined, but you have to be careful. This plus is in that this plus we are defining in V tensor product V star actually. Okay? While this plus is where? This plus is in R. Okay? This plus is in R because they give you numbers again. You getting the point? So maybe it would be fun to think that what would be the meaning of multiplying a lambda with the tensor product of beta and alpha and operating it onto u. Then it should be,
lambda term.
as per expectation, lambda times
Beta plus
beta
beta cross of
tensor product alpha
of u.
of u. Okay? And we can show that this tensor product V star is a vector space. So it's a vector space. Okay?
The field R ही रहेगा इसकी भी.
Everything is in R.
सर हम R में हैं या होता ही R में हमेशा?
नहीं हम like you can take it to the abstract field actually. ठीक है? For example, if you are doing, for example, if you read this book by Garrett O'Neill, but it's called the Semi-Riemannian Geometry. So it defines this very abstractly. So instead of taking vector spaces, it takes modules actually, and takes field as an abstract field. So you can generalize this whole thing. It's fine. The question is, if you understand it once for one structure, the generalization is not difficult. You can make sense of it because we are not changing the most of the things. We are changing the some structure. A few things would be allowed, few things would not be allowed. You have some flexibility, you will not have some flexibility. That's it. Okay? Next question. Okay? Next question. What would be the basis of V tensor product V star and star?
Tensor product of basis of the dual spaces.
Mm-hmm.
Tensor product of the basis of the dual spaces.
Tensor product. That's a very good intuition actually. So for V, you have these bases which you call EI. And from these EI you are creating. So you can have a basis of V star which has nothing to do with the EI actually. But at the moment we want them to be connected actually in a certain way. Okay, so I'm not just taking any random arbitrary VI. So these are the epsilon i's such that when you operate them on EI, they give you the Kronecker delta. Okay? Question. From these, can I have the basis for V star, V star? The answer, as intuitively Abdul Latif gave, why not take the tensor product of epsilon i's with itself? In other words, the basis of this is going to be all possible tensor products that you can do with the epsilon i's actually. So epsilon I tensor product epsilon. Okay? What do you mean by that? So in other words, for example, if this guy is three-dimensional, so it's like four-dimensional, like relativity. Okay? So you're going to have basis epsilon naught, epsilon 1, epsilon 2 and epsilon 3. Okay? So what are possible products of these? So how many possible products you can have from these actually?
450.
So it's going to be 2, not 4. So it's like, okay. So it's like, so you have two boxes to be filled here. So apply the combinatorics, huh? Okay, and what vector you can put here? How many choices of vectors you have here? So you have 4 here. And so you have 16. So it's going to be a 16-dimensional vector space actually. You have to think about it. The dimension is increasing actually. So it's like when you are taking the tensor products, the dimension is increasing. Okay, so it's like one vector could be epsilon, epsilon, and then epsilon, 1, and then 2, and 3, and 0, and 1, and 2, and 1, and so on. And so on. All these are what do you call bases of sequences. Okay? What next thing you will be interested in? I'll be interested in that how these bases are going to work on an abstract vector. So it's like on an abstract ordered pair. Okay? Because if you know these, then you can take a bilinear form and write them in the terms of these bases. This is what that we like to have actually. Okay? So take epsilon I, tensor product epsilon j, and operate it on u and v. Okay? And I and j are what? They could be anything. 0, 0, 1, 0, 2, 0, something like that. So this would be same as the tensor product epsilon I and epsilon j operated onto u. So I can write u in the summation convention. So it is going to be, ui ei, not I, but maybe ua ea. Okay, and this guy would be VA and EA, because both are vectors. They are elements of V and V, not the co-vectors. So if you have the case of this, then when you are operating this onto an ordered pair, so the definition tells me that you need to take what? You need to take the epsilon j and operate it on UAEA multiplied by epsilon I and operate it on VA and EA. Okay? So this guy is going to be, so these are numbers. So you're going to have UA and then epsilon j operated onto EA, and this is V. Okay, so not put A but put a V here. Let's not repeat the index. Summation convention, it shouldn't be repeated more than once. More than 2 times.
So we had beta at the first place. So beta of u आया था. अभी epsilon I है तो epsilon I ही आएगा.
Okay. So I can put an I here and I can put a J. Doesn't matter. Doesn't matter. करेगा. You have to care the definition.
Yes, sir.
Okay. I and VB and epsilon J. Okay. And what?
Small ev.
E. Okay. So what are you gonna get? UA. And this will be the Kronecker delta IA and VB and Kronecker delta JB, and you're gonna get what? So you have UR, okay, multiplied by VJ. Okay, this is going to be the okay? So in other words, this would be 1 if I or A is same as I. Okay? Because this is fixed actually. A is same as I. So when this is I, so this must be also I actually. So this will be 1 and you're going to get UI. So what is the output? Think about it. So this tensor product is, when it's operating onto an ordered pair, it's giving me the product of ith component of U and jth component of G actually. Okay? Ith component of U and the jth component of V. Okay? So this is what the key thing you have to keep in hand. You have to kind of make yourself comfortable with these symbols actually. You have to get into this dirty game, I know symbols are trouble. but you know, this is what the demand is. So it's not difficult. If you are stick on your, if you are firm at your definitions, it's pretty simple. कोई मुश्किल नहीं. Is it making sense? So now let's take beta tensor product alpha and operate it on UNV, and let's see what we